All right, welcome back. So 9.6 is a really fun and interesting section, and it's about combinations, which is what we've been talking about. But now we can have repeated elements. So it's not like we're picking out of a certain number of things and then we can't have them anymore, but we can always have another one of what we just picked. So I've got an example. Maybe you've been to the supermarket, Safeway or Fred Meyer, and you go to get coffee creamer or milk or juice, and they're in the coolers. And as soon as you take one out, another one just falls in to replace it, so that you can buy 3 orange juices if you want to, or you could buy 3 different types of juice or coffee creamers. This is my 12th video that I've made today, which seems ridiculous, but I have had a cup and a half of coffee, so I should be okay. And I'm going to do a coffee creamer problem, even though I think coffee creamer is awful and it's nasty. It's terrible. You shouldn't drink it. Coffee is good and healthy and amazing, and you should just put some half and half in it and leave all of the sugar and the creamers and the bad stuff out. But that really has little to do with this problem, other than suppose we are going to Safeway and there are 5 different types of coffee creamers. I know there's more than that, but suppose there were only 5 and we're going to buy 3. So I've got A, B, C, D, E representing the 5 different types of coffee creamers, but we could just buy 3 E's in this case, because I'm going to do a problem with combinations where repetition is allowed. So I could buy 3 D's if I wanted to. I could buy 2 B's and a C, because every time I choose one, pretend like there's another one behind it that falls into its place, and I still have the chance to choose another one again. I'm going to show you 2 different ways of how to do a problem like this. One is with the formula that's in our book, but then there's another method called the stars and bars method that I really like, and it actually turned this problem into the Mississippi problem. It makes it a lot easier. So let's give a look. Suppose we weren't sure what to do, but we just wanted to pretend like we were making some selections. And so I'm going to buy 3 out of these 5 choices. So let's say that we just chose C. So C comes down, and that's one of my choices. But even though C is now gone, there's a new C that takes its place. So if I wanted to, I could choose C again, but maybe I decide not to. Maybe I pick E. And so I picked E, but another E fell into its place, so that now what I have is the opportunity to choose any of the coffee creamers that I want, and maybe I do choose another E. So I choose coffee creamer C and then 2 E's, and that's a way of doing this. Well, the interesting thing, if you look at this, I actually was able to choose 3 out of how many options? 1, 2, 3, 4, 5, 6, 7. So there were actually 7 options, because when I chose one, another replaced it. And I filled up my 3 choices out of the 7 that I chose from, because I always got to choose another one. And in reality, then I had, again, 1, 2, 3, 4, 5, and then 6, and then 7. And I chose 3. So 7C3 is a way of understanding this question, but it's not the only way. It's a pretty simple way. Yet the problems can get complex enough that I think I like this other way. It's called the stars and bars method. I'll use maybe a different color, maybe green. And so what we would do is, since I have 5 different coffee creamers, and we'll still end up with the same number, by the way, the same answer, I could create what are called bins for all 5 coffee creamers. So I'm going to write 4 bars, and this bin to the left of this first bar is going to represent coffee creamer A, and then B will be in here, and C will be here, and D will be here, and E will be here. And now I'm just going to put, well, I'm going to select 3 coffee creamers. So maybe I select a D. I'll put a star there to represent D, and maybe an E and maybe a B. So what I really have is a code of two different types of characters. I've got bar star bar, bar star, bar star. So if I wanted to represent buying one creamer B, one of D, and one of E, I would have bar star, bar, bar, star, star. It's, again, just a list of characters. And in fact, every way that I rearrange a list of these characters, 4 bars and 3 stars, would be a unique way of buying 3 coffee creamers with 5 to choose from. So for example, star, star, bar, bar, star. And now if I spread it out and make it look like this, what this actually means is I'm not going to buy any A's. I'm not going to buy any B's. I'm going to buy 2 C's because every star represents a purchase. I'm not going to buy any D's. That's between those 2 bars. And I'm going to buy 1 E. Well, that is a unique code, that bar, bar, star, star, bar, bar, star, that represents a particular purchase. So all I really have to do is rearrange 1, 2, 3, 4, 5, 6, 7 characters, bars and stars. And the way to rearrange 7 unique characters would be 7 factorial. But this is like the Mississippi question because I actually have repeats of the bars. There's 4 bars and I've got repeats. So I divide off by 4 factorial. And then there's actually 3 stars. So I divide by 3 factorial. It's just like the Mississippi question because I've got an arrangement of characters, but that arrangement is a particular code that means a purchase of 3 coffee creamers out of the total that I have. But notice this calculation right here is exactly the same as what the formula for 7C3 would be, which would be 7 factorial over 3 factorial times 7 minus 3 is 4 factorial. So the stars and bars method led us to this being the number of ways to do the problem. And just the formula, which I can write down in general in a minute, led us to the exact same answer. So if you plug this in, or you could do it by hand, it's not that hard. If you plug this into your calculator, that would be the number of ways to buy 3 coffee creamers out of 5 types if it's okay to buy more than one of the same type. Now, if I erase this formula here, if I have n items, and we're going to choose groups of size R, so we had 5 items, choosing groups of size 3, with repetition allowed, then what I'd have to do is I'd have to use that counting feature, the combination counting feature, but I would have to do n plus r minus 1 CR. N plus r minus 1 CR. So I'm choosing groups of size r out of a total number of choices of n plus r minus 1. That's why when I had 5 choices, that would be n, plus r equals groups of size 3, that's 8, minus 1, that would be that 7 CR, which is exactly what we decided. That 7C3 was the way to calculate the number of purchases of size 3 from the 5 different types, given that repetition is allowed. So a fun problem. We'll do some more examples as well. I'll see you in the next video.